So, in the last lecture we discussed about the structural damping and we said that this value can vary from 0.2 to 0.5% of that of the critical damping. In addition to this, we also have hydrodynamic damping, which has got two components. One is the radiation damping, other is the viscous damping. The radiation damping essentially depends on, it is evaluated using the potential theory and it depends on frequency and submergence of the structure. Literature show that this damping is close to about 0.1% for cylindrical dampers. You can see here that the damping estimate is complex because of contributions from the structure and contributions from the loads, or I should say type of loads. Further, there is one more complication added to this. If the structure becomes flexible, or I should say compliant, or I should say non-stiff structure, non-rigid structure, then there will be damping associated with the structural vibrations also. Therefore, interestingly, the damping estimate in marine structures is given by a different algorithm by Aravind Nace and Torger-Mohr. This reference available in the website of NPTEL, you can see this. What Aravind and Torger said are the following. They say if you want to find any marine structure in a wet condition of damping, then I can use a different equation. So, associate the value of dry damping of the structure with that of the mass of the structure in dry state and frequency of the structure in dry state, and find the ratio of this mass frequency in the dry state to that of the wet state and multiply this ratio with that of the dry damping ratio. You will get the damping ratio which includes or which involves the submergence effect also. So, I call this equation number 12. which we are continuing. Having said this, the literature show that an approximate value of 2% for first 3 modes of a bottom supported structure is alright. So, value of 2% is what is recommended in the literature for a bottom supported structure. For example, fixed jacket platform, gravity based structure, etc. So, one can use 2% for the fundamental mode and additional 2 modes, that is first 3 modes you can use 2% as the damping, which can account for radiation damping, which has an effect of the submergence as well as the frequency. You have frequency content also here. Now let us talk about the wave spectra. We are on the verge of discussing about the environmental loads acting on marine structures. We started with the hydrodynamic loading, we moved on to the damping estimates, we will talk about now the wave spectra, then we will move on to the wind loads. Then after wind loads are completed, we will talk about ice loads and earthquake loads and current loads. So, we will have a comprehensive summary of what are the different profile of loads acting on the marine structure, then we will get an idea which load will combine with what to find out the ultimate strength capacity of any member of a marine structure. So, we will talk about wave spectra now. There are big confusions arising for wave spectra, there are different spectrum recommended by literature, we will quickly see all of them because this lecture is not focusing on the hydrodynamic aspects of working out or deriving the wave spectra. We are only looking at in the designer's perspective which wave spectra should I use for design of marine structures and why should I use it and what are the important critical points of the respective wave spectra. Wave spectra actually is got a 2 directional wave spectra which I call as S plus omega theta is a function of 2 factors. Essentially it is a product of these 2 factors. So, S plus omega theta is S plus omega and d omega theta, equation number 13. Where d omega theta total integral will be unity S plus omega refers to the wave spectrum and d omega theta refers to the directional distribution of the wave energy. This is a general combination of any spectrum which is being used in marine structures which has got a product of the wave spectrum multiplied by the directional energy distribution. So, the most common form of the wave spectrum being used in marine structures is Pearson Moscow spectrum. Famously called as PM spectrum. S omega is A omega phi exponential minus B by omega 4, call this equation number 14. So, the PM spectrum essentially depends on two parameters, A and B. A and B are actually constants. Depending upon how these constants are defined, there are different forms of the spectrum available in the literature. For example, A is given by alpha g square, where alpha is known as Phillips constant, which is 0.0081. B is 1.25 omega p to the power 4, where omega p is called peak frequency at which S plus omega is maximum. Now, we all know that in an open sea state, sea waves are generated because of the wind. Okay, it is wind driven spectrum actually. Wind driven spectrum. And therefore, if we really wanted to find out the peak frequency at which S omega will be maximum, then you must also specify what is that wind condition which makes omega p maximum. So, omega p refers to actually omega of, I say u, which is actually a function of mean wind speed measured at 19.5 meters above mean sea level. So, you measure a mean wind speed at an elevation about 19.5 meters above the still water level, and that wind speed will be giving you omega p, and that omega p is what I will use in the parameter of B here, and of course A is a Phillips constant based value. I will get a spectrum which is generated, which for example you can plot now the spectrum for every value of omega. Okay, so S eta eta will be on the y axis and omega will be in the x axis, you can plot a spectrum I will show you the spectrum slightly later, but this is how it is done. You can see here in the conventional PM spectrum there is only one parameter which governs the spectrum, is it not? What is the parameter which is governing the spectrum? What is the parameter which is governing the spectrum? The parameter which is governing the spectrum is omega p, because that is the only value which is controlling B. A is of course a constant. So omega p on the other hand is the based on the mean wind speed at a specific elevation. So this is controlling the whole generation of the spectrum. Now this spectrum is further modified, which is also used and applicable to marine structures. That is called modified PM spectrum. In this case the constant A is changed as I call the equation number 15, where omega p has the same explanation as you have here, but Hs is what we call as significant wave height. So now PM spectrum, when it is modified, it has got two parameters now. Now it is governed by two parameters, namely omega p or average mean wind speed at a specific elevation on the MSL or above MSL, and significant wave height. One more additional spectrum is also given by International Ship Structures Congress, ISSC. In this case A and B constants are redefined as call this equation number 16, 17. So in this case omega bar is defined as a ratio of different moments m1 by m0, this is called average wave frequency. Where m0 and m1 are different spectral moments, where m0, m1 are called spectral moments, and they can be given by There is one more spectrum which is very commonly used in the literature for analysis and design of marine structures is the John-Swab spectrum. But you will see John-Swab spectrum has got a specific parameter which when middled with will land up in modified PM spectrum, we will see that. Okay. So, D is John-Swab spectrum. This has got exactly an abbreviation where it has been applied, so it is not somebody's name, okay. It should be written in capital, these are all expanded terms actually, okay. This is the classical John-Swab spectrum. The value gamma is called pickedness parameter and it is in the exponential form actually. Exponential means e power. So, this A omega is again in exponential form actually, okay, it is not simple. Equation 20, where sigma bar has got two values is nothing but equal to sigma A of 0.07 for omega less than the peak frequency is equal to sigma B. I can put sigma bars here because that is what the literature says, sigma bar A and sigma bar B 0.09 for omega greater than omega P. This equation is 21. I have not still explained the spectrum completely, we are only talking about the pickedness parameter which is again an exponential form where I am talking about a omega as a variable, here I am explaining the variable, I am coming back to the spectrum again, we have alpha bar here, of course omega p already has been explained. Alpha bar depends on the fetch parameter and the mean speed. Which can be given by natural logarithm of mu. I call C question number 22. As I said at the beginning, nu is a pickedness parameter which varies from the value of 1 to 7. At a specific value of this, the Jones-Spec spectrum will become Pearson's mass wave spectrum. Let us try to plot it here and show. I will remove this. So, typical value of mu at 3, this is how Jones-Spec spectrum will look like. When you substitute the pickedness parameter as unity in the Jones-Spec spectrum equation, I will get the Pearson mass wave spectrum. Which will have a peak at 3 and a broad end spectrum. This is PM spectrum, I should say mu equal to 1. So, the figure shows essentially the plots of Jones-Spec spectrum for nu equals 1 and 3. The pickedness parameters 1 and 3, it shows two different spectrums. So, now PM spectrum is a modified version of Jones-Spec spectrum where the pickedness parameter assumes a specific value of unity. Now, the pickedness parameter nu is also given by an equation which has got two values. It can be equal to phi for Tp by root Hs less than or equal to 3.6. Tp is nothing but 2 pi by omega p. Omega p is the peak wave frequency, is the period of the peak wave frequency. Tp, Hs the significant wave height. If this ratio is less than 3.6, you must use nu as phi in the Jones-Spec spectrum. otherwise exponential value of for Tp by root Hs greater than 3.6. These are equations number 23. So, we will interestingly see that S plus omega multiplied by d omega theta was giving me the spectrum, the wave spectrum, which has got the wave spectrum multiplied by the distribution of the energy in terms of frequency and direction. Generally, for practical design considerations, in marine structures, the frequency dependence is ignored. You consider only the theta, only the directional dependence. So, I should say d omega theta is approximated to d theta for design purposes. We neglect the frequency dependence of the function. This about the wave loading. Let us talk about the wind loading and see what are the complications present in the wind loading and what is the spectrum which defines the wind loading, as we have seen the spectrum defining the hydrodynamic loading, and see how the complications of wind loading is handled in a simplified manner in the literature by providing what is called aerodynamic admittance function. We will see how this can be derived. So, we will talk about now the second loading, which is wind forces. Do we have any questions on the wave loading? We have discussed about the wave loading, we have seen what are the kinds of damping arising from the wave loading. Fundamentally we saw how the loading is acting on the marine structure. Then we saw the water particle kinematics defined by the simplified Airy's theory, and what are the stretching modifications suggested by various researchers in the literature, and why these modifications are implemented necessarily in a Airy's form, because Airy's form will agree or accept the values only till the MSL, whereas the variable submergence effect is not accounted for. The second important issue is what we had is the phase difference or the phase lag between the members. Offshore structures have larger dimensions in terms of the planned dimensions. So, the center to center leg spacing can be as high as 120 meters or 100 meters compared to the wavelength. If you work out the phase lag or the phase difference, it may come to 1.2 times of pi, which can have a negation effect on the loading. So, that is one of the design parameters of which the spacing of the legs are fixed in an offshore structure, so that the force on the members are getting cancelled to each other. So, that is the phase effect on the loading. Of course, when we talk about the loading, we are amounting to what we call as a spectrum. We found out there are different spectrums available in the literature, and we have seen the commonness between the spectrums, and one parameter defined spectrum like PM spectrum, or the modified version which has got two parameters, one is omega p and the other one is significant wave height. And then we have also seen how Johnson spectrum can be modified down to bring down to phase and mass wave spectrum. Therefore, people have used in marine structures commonly the Johnson or modified PM spectrum for finding out the force on the marine structures. This is about aerodynamic loading. Let us come to the wind forces. Now wind forces acting on members of marine structures actually arise from a complex fluid dynamics phenomenon. Therefore, it is very difficult to compute these forces accurately. That is the catch here. So, it is very difficult to compute these forces accurately or with high accuracy. Then what is done in engineering? So, most accepted and widely used engineering practice for computing wind forces has the following assumptions. 1, when stream of air is flowing with a constant velocity v, it will generate a force on the flat plate located orthogonal to it. That is normal. When the plate is placed normal to the direction of flow of wind, it generates or exerts force on this plate. This force will be proportional to A V square, where A is the projected area and V is the wind speed. Now, the proportionality constant I should say does not depend on the projected area. Remember this, very very important. Now, in these assumptions we have got 3 important keywords. 1, we are always trying to work out the force on a plate which is flat. If it is curvilinear, then we have no idea how this force will get modified. Then there should be a factor to get multiplied with this, which will account for the curvature of the plate or the member. The second is, plate should be always placed normal to the flow direction. If it is inclined, then you must use appropriate projected area. For example, if this is my wind flow direction, if this is my member in plan, this is my member in plan and this is one length and of course the height which is normal to the board, and I call this as my projected area because the axis of the member is normal to the directional flow of wind. If the member is inclined, whose axis has a value of, let us say, theta with that of the direction, then I must use equivalent area of projection will be A sin theta. Is that okay? Okay. this is the wind. So, it is always computed normal to the flow velocity or the direction, and of course, this force generated will be proportional to AB square, and that proportionality constant is independent of the area of projection. That is very very important. This has been ascertained and proved by wind tunnel testing in experiments. It does not depend on the projected area, it depends on some other factor, we will talk about that. Is that clear? Having understood this, as we all know, the wind force is proportional to the wind pressure. I should say the net wind pressure, which is given by half rho Cw V square. Equation number 1 in the wind forces. Rho A is the mass density of air, which is 1.25 kg per cubic meter. Cw is the wind coefficient, I should say wind pressure coefficient, and of course V is the velocity of wind. Interestingly, it is important to note that the mass density keeps on increasing due to the water spraying above the MSL, that is what we call as splash zone. So, this keeps on increasing. Okay. So, the estimate what you make with this number as the pressure acting on the member is not accurate whenever you are talking about members in the submersion zone or in the splash zone, and that splash can happen to a value of 20 to 30 meters above MSL. You see, it is as high as this value. Okay. Now, the total wind force is given by Pw into A, where Pw is what I computed from equation number 1, and of course A is a projected area. Which is normal or orthogonal to the direction of wind. If the member is inclined, then you must find out appropriate projected area which is orthogonal to the direction of flow of wind. Now, one is interested to know how the Cw, that is wind pressure coefficient, is obtained. Cw is obtained based on wind tunnel test experiment. and this value varies from 0.7 to 1.2 for cylindrical members. Of course, this is dependent on the Reynolds number. When we talk about estimating wind forces, wind velocity has got two components we must understand. Natural wind has got two components. One is what we call as the normal or the mean wind speed, which is a statistical parameter. Statistical, no, it is static, it is not dynamic, I should say static parameter. The other one is the gust wind, which is the fluctuating component which is the dynamic parameter. So, I can now say velocity of wind can be mean plus V of t. This is the mean wind speed and this is the gust component. V bar has spatial dependence only along the height. This is very important. It varies with along the z only, along the z axis. Whereas V of t, the gust component, is homogeneous with respect to space and time. It varies, but homogeneous. So, therefore, wind force generated by the wind on members of marine structures has got two components. One is called as Fd, other is called as Fl, the drag force and the lift force, which is half rho Cd A Vz square half rho Cl A Vz square. The only variation is Cl and Cd, the coefficient is varying. This acts parallel to the direction of wind, this acts normal to the direction of wind. So, this is called drag force, this is called lift force. So, we stop here now, we will continue in the next lecture what is the spectrum which would advise me to compute the wind forces on the members and how the complexity and randomness of wind loading can be handled in the literature to make it simple for computing the force on members using aerodynamic admittance function. Okay, so that will be the target, plus we will also discuss about the ice load and the earthquake load coming on members of marine structures. Therefore, we will comprehensively discuss the environmental loads coming on members.